AI is starting to close the loop between seeing, planning, and acting. This week's biggest shift is that embodied models are no longer just recognizing scenes or predicting motions, they're learning to recover from mistakes, generate training data from pure digital assets, and even use language as the control layer for long-horizon robot behavior. That matters because it removes some of the most expensive bottlenecks in robotics: teleoperation, action labeling, and fragile hand-coded planning. Here's what that means for real robots, sim-to-real transfer, and the race toward general physical intelligence. Let's explore the first paper, Embodied R1, 5 Evolving Physical Intelligence via Embodied Foundation Models. Embodied R1 5, developed by Tianjin University with Tencent Hanyuan as a collaborator, is a unified 8B parameter embodied foundation model that merges embodied cognition, task planning and correction, and embodied pointing into one architecture for physical intelligence. The paper's main technical contribution is a 1.5B token training system built from 34 datasets plus 3 automated construction pipelines: ER15, spatial for tabletop 3D scene annotation, ER1.5, correction for failure-aware planning and recovery, and ER1.5, pointing for referring expression grounding, functional affordance grounding, and visual trace generation. Training uses a 2-stage recipe: supervised fine-tuning followed by reinforced fine-tuning with a multitask balance RL method that combines difficulty-aware filtering, dynamic filtering, and global batch reward normalization. On evaluation, Embodied R1.5 reaches state-of-the-art on 16 of 24 embodied VLM benchmarks and averages 70.4% across the 21 main accuracy benchmarks, outperforming Gemini, Robotics, ER1.5 by 17%, and GPT-5.4 by 21.7%. The strongest gains appear in pointing and location, where it averages 72.8% and leads on all 9 pointing benchmarks, including 82.9% on PartAfford and 80% on RoboAfford. The model can also be fine-tuned into embodied R1.5 VLA with only a small amount of action data, reaching 92.4% on SimplerEnv, Google Robot, visual matching, and 97.3% on Libero without action pre-training. In zero-shot real robot tests, the PGC Planner Grounder Corrector Loop enables fully autonomous execution on tasks such as tool affordance, cup disassembly, and door opening, with 100% success on pick and place and tool affordance. Let's explore the second paper, Grail generating humanoid loco manipulation from 3D assets and video priors. Grail, from NVIDIA and UCLA, is a fully digital pipeline for generating humanoid loco manipulation from 3D assets and video priors, designed to avoid physical scene rebuilds, teleoperation, and motion capture until deployment. It first constructs a metric 3D scene with known camera, scale, object geometry, and a robot-proportioned character, then uses video foundation models and OpenAI's ChatGPT-assisted prompting to synthesize interaction videos, reconstructs metric 4D human object trajectories with Genmo, Ylor, Foundation Pose, Moog 2, SAM2, and interaction-aware losses for projection, depth, and contact, and finally retargets motions to a Unitree G1 through task general trackers built on the Sonic whole body controller. The resulting asset condition dataset contains over 20,000 sequences spanning pickup, whole body manipulation, sitting, and terrain traversal generated from 1,000 object assets and 1,000 terrain configurations. On a shared 2.0 object benchmark, Grail reaches 0.008 contact distance, 0.9% penetration, a 3.58 interaction score, and 88.9% physical executability success rate, outperforming Davi, Choi's, and HOIDIF. For downstream control, the full tracking system achieves 81.4% success with 0.135 object position error and 41.8 local MPJPE, and its sim to real egocentric policies transferred to hardware with 84% pickup success on diverse objects and 90% stair climbing success on a real Unitree G1. Let's explore the third paper, World Language Action Model for Unified World Modeling, Language Reasoning, and Action Synthesis. World Language Action Model, or WLA, is a new embodied foundation model from SJTU and collaborators that unifies world modeling, language reasoning, and robot action synthesis by predicting a semantic textual intention, a future visual state, and executable action chunks in one autoregressive transformer. Unlike diffusion-based world action models and typical vision language action systems, WLA uses meta-queries plus a dedicated world expert to separate compact latent dynamics from fine-grained frame prediction, then lets an action expert condition on that latent transition. This makes the world module removable at inference while still supporting test time scaling through imagined rollouts and value-based trajectory selection. The WLA0 prototype uses two B-active parameters for inference, reaches about 40 milliseconds latency on an NVIDIA RTX 5090, and removes the need for embodied pre-training. On RoboTwin 2, WLA0 scores 92.94% on clean scenes, and on RM Bench, it reaches 56.5% average success, nearly doubling the strongest prior memory-based baseline. On Libero, it achieves 98.6% average success, rising to 98.9% with test time scaling. The paper's key claim is that textual subtasks are not just instruction paraphrases, but the control interface for long horizon progress tracking, memory, and recovery, enabling cross-embodiment video-only task acquisition without action annotations. That's a wrap on today's AI paper highlights. Thanks for watching.